You know that thing when you see those tiny specks of dust just dancing in a sunbeam. Well, for almost 200 years, we thought we had the perfect explanation for why they do that. In this explainer, we're going to dig into why that long-held belief might be completely and utterly wrong.
Yeah, it's a scene we've all witnessed, right? A quiet room, a single ray of sunlight cutting through the dark, and inside it, this silent little ballet of dust motes. Science gave us an answer for this centuries ago. But what if that explanation, the one you find in basically every textbook, just doesn't add up?
So this little dance has a proper scientific name, Brownian motion. It was first documented way back in 1827 by a botanist named Robert Brown. He was looking at pollen grains in water, and he saw them just jittering around like crazy. He knew they weren't alive, so what in the world was pushing them? And the story we were all told is pretty simple. The idea is that the dust particle is basically in a microscopic mosh pit. It's getting bombarded from all sides by trillions of invisible, super-fast air molecules. And every now and then, just by pure random chance, a few more molecules hit one side than the other, giving the dust a tiny nudge. Sounds perfectly logical, doesn't it? Well, this is where our story takes a very sharp turn. Because when you actually sit down and run the numbers on that idea, the whole classic theory starts to fall apart. And I mean, it falls apart spectacularly. So here's the crucial calculation. For a single tiny water molecule to smack into a pollen grain hard enough to move it, even the tiny amount we see under a microscope, that one molecule would have to be traveling at over 32 million meters per second. Let's just put that into perspective. That is more than 10% of the speed of light. It's an absurdly, impossibly high speed for a single molecule just bouncing around in your living room. Okay, let's put those two numbers right next to each other. The speed required by the old theory is over 32 million meters per second. The actual average speed of a water molecule, it's about 590. This isn't a small discrepancy, folks. The speed needed is tens of thousands of times faster than what is physically possible. And hey, don't just take my word for it. The source material puts it pretty bluntly. The speed needed for this classic theory to hold water is, and I quote, well beyond the limits of physical plausibility. So, the idea of a single molecule doing all the work, that's out. But all right, I know what you're thinking. It's not one super molecule. It's a whole bunch of them hitting at the same time. And that's the other part of the explanation. It's a fair question, for sure. But to get that same tiny nudge using molecules at their actual normal speed, you would need more than 54,000 of them to all slam into one side of that pollen grain at the exact same instant with nothing hitting the other side to cancel them out. The odds of that kind of perfectly synchronized molecular assault happening are, for all practical purposes, zero. It's like flipping a coin 54,000 times and getting heads every single time. It just doesn't happen. So the old theory seems to be dead in the water. What's really going on? So if it isn't a molecular mosh pit causing the commotion, what is? Well, the theory we're exploring here proposes something totally different, a new kind of fundamental force. The researchers call it trans-impact. And here's the core idea. When an atom absorbs a bit of energy, say from that sunlight, an electron inside it gets excited and jumps to a higher orbital. This jump instantly makes the entire atom expand, like blowing up a balloon in a split second. This image breaks it down perfectly. On the left, you've got two atoms just hanging out. In the middle, one absorbs some energy and bam, it instantly expands, getting right in its neighbor's personal space. This creates a powerful repulsive force that, as you see on the right, shoves the other atom away with some serious oomph. So let's just run through that one more time. An atom absorbs energy, an electron jumps up, the atom's volume rapidly expands, and this sudden expansion creates an explosive push, shoving anything next to it away. This, the theory argues, is the real engine behind Brownian motion. To make this a little more intuitive, the source uses a fantastic analogy. Think about a kernel of popcorn. It soaks up heat, and then suddenly, pop, it explodes outwards, pushing everything around it. A trans-impact event is like a microscopic version of that, happening constantly, all around that little speck of dust. But here's the thing. This idea isn't just about dust. If trans-impact is real, its implications could be enormous. We might have to rethink some pretty fundamental concepts in physics that we all thought were settled science. Take a look at this device. It's called a Crookes radiometer. It's that little windmill on a glass bulb that spins when you shine a light on it. For over a century, no theory could really explain why it spins the way it does. Specifically, as this graph shows, its acceleration is at its absolute maximum the very instant the light hits it. Transimpact predicts this perfectly. The electron jumps are instant, so the push is instant. Older theories just can't account for that. But the implications get even bigger. The whole theory of transimpact leads to a really radical question. What if our most basic understanding of what temperature is fundamentally flawed? We're all taught that temperature is just a measure of how fast atoms and molecules are jiggling around, their average kinetic energy. More jiggling equals a higher temperature. Seems pretty straightforward. But here's the problem. If that were the whole story, our kinetic theory should be able to perfectly predict how much energy it takes to heat up any gas. And it can't. As this chart shows, for more complex molecules, the theory's predictions get more and more wrong as the number of chemical bonds goes up. It's like energy's going somewhere that the old theory just doesn't know about. The transimpact theory offers a wild solution. It suggests temperature isn't really about the motion of atoms. Instead, it's a measure of the potential energy stored inside their chemical bonds, like tiny compressed springs. The jiggling motion we see isn't the cause of heat. It's just a side effect of that stored energy being released. This would perfectly explain why molecules with more bonds can store more heat. So let's just recap the big takeaways here. If this theory holds up, it gives us a brand new cause for Brownian motion. It gives us a much better explanation for that weird spinning radiometer. It gives us a totally new way of understanding temperature itself, and it even suggests a new mechanism for phase transitions, like ice melting, arguing that it's transimpacts breaking bonds apart, not just vibrations. And all of this leaves us with one final, fascinating question. For nearly 200 years, the explanation for dancing dust seemed completely settled. If it turns out to be wrong, it just makes you wonder, doesn't it? What other fundamental truths of science are just sitting there, waiting for someone to take a second look?